times 10 to the power minus 6 meter cube. So therefore, I'm just going to write down here. Okay, so therefore, okay, because all my informations are here, okay. So the shear xy at point B is equal to 25 times 10 to the power 3, 219 times 10 to the power minus 6. Okay, 219 10 to the power minus 6 divided by 40.8, and our y and our thickness is 7.24. So this is 25 power 3 times 219 power minus 6 divided by 40.8 power minus 6 divided by 7.24 power minus 3. So it's 18.535 times 10 to the power 6 Pascal, and it is flowing in this direction, as you can see. Okay, so it's flowing in this direction over here. Okay, so that is the direction that we have. Right, so now we're going to transpose everything into the element. Okay, so we're going to draw for element B. Anyone, any questions so far? Okay, I don't hear anything. No one have question. So I'm going to copy this image over here. Right. Okay. So now we are going to draw our element. Okay. So we know that this is our X. This is our Y. And this is our Z. Okay. So I'm going to draw element B. Okay. So our element B has a normal stress coming down in compression. And this compressive stress about the Z direction is minus 14.948. Minus 14.948. Now the shear, because 25, let me blow this up. Okay, we know that the shear flow at point B is traveling in this direction. Right? Can you see the pink arrow I've just drawn? So when that's the case, this is the direction of the shear. Okay. So for this case, the shear will be equal to 18.535 times 10 to the power 6. Okay, so it's 18.535 times 10 to the power, or I'll just call this megapascal. Okay, so this is our element B. Okay, stresses. Okay, so I mean element B and the associated stresses that are acting on element B. So on Tuesday, let me put element A. So this is our element A. Okay, so this is our element A. And today we have done our element B. Okay. So you can see the stresses acting on element A and B, and the transformation did not change. So this is still our X. This is still our Y. And this is still our Z for both. Okay. Right. So the question, I'm going to do a step further. Okay. We are going to determine the principal stresses and maximum shear stresses, okay, for element A and element B using, okay, 3D Mohr circuit. So I'm on Mohr circuit, don't worry yet. Okay, I'm going to do 3D Mohr circuit. Okay, and probably on the second hour for this class, I will teach 2D Mohr circuit and 3D Mohr circuit. Some of you I know have not taken P02 before. You will have not know 2D Mohr circuit. It's okay. Okay, I'm going to teach you as if you have no knowledge on Mohr circuit. But I'm going to show you now, okay, how to construct 3D Mohr circuit. So constructing 3D Mohr circuit, the knowledge required is 2D Mohr circuit. Okay, and I'll show you why. Okay, so let's consider element A. Okay, let's consider element A. So this element, I'm going to bring this element in. Let me see how much space we have. I think we will have enough. I hope. Okay, so this is our element A. So what does our element, so I'm going to call it, so if we have to draw a transformation first. So this is X, this is Y, and this is Z. So I'm going to call this surface over here our point X, right? This surface over here, our point Y, and this surface over here for our point Z on Mohr circle. Okay, so seeing with what we have, what we know is that stress Z is equal to 28.852 megapascal, right? Then we have shear Zx is equal to minus 1 point or 1 I'll call it minus 1.608. Okay, later I'll tell you why. Megapascal. Okay, and then what we have is stress X is equal to 0. Stress Y is also equal to 0. And then the rest of the shearing direction, our shear XY, which is equal to our shear YX, this is equal to 0. And our shear YZ is equal to shear ZY is also equal to 0. Okay, so now we are going to construct 3D Mohr circuit. Okay, probably in 2 weeks time I will explain, or next week, possibly next week, I will explain why we have to do this in 3D Mohr circuit and not 2D. Okay, right, so let's construct our axis first. Okay, so I'll write down here this is 3D Mohr circle. Okay. So on Mohr circle, this is our normal stress. Okay. And then I'm going to sketch our shearing stress. Right. So this is our shearing stress. Element rotate clockwise on the top half. This is 0. Element rotate anti-clockwise. Okay, so this arrow shows element rotation due to shear stress or shearing stress. Okay, so I'm going to go 5, 10, 15, 20, 25, 30. Okay, then will be the scale has to be the same: 5, 10, 15, 20, minus 5, minus 10, minus 15, minus 20, minus 5, and minus 10. So our stress Z is at 28. So we draw a vertical line, okay, and 20, 25, 27.5. So this is about 20, wait, 25, hold on. Oh, I divide by 2. Silly me. It's okay. So 28. So this is about, it's a sketch. Okay. So this is our normal stress Z line. Okay. And our normal stress X line and stress Y line is on this 0 line over here. And our shear is 1.608. Okay. So 1.6. I'm going to sketch this out. I've chosen very bad scale. I know that. Okay. 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 So I understand that we have drawn this as negative shear, but we have put a positive and negative shear on our Mohr circle. And as I said, I will explain to you why. Okay. Now, let's look at point Z now. Okay. So point Z is as a tensile of 28.852. Okay. So this is our stress Z. And the shearing stress is going in that direction. Okay. So if you put your finger on the center, right, this shearing stress over here were this shearing, hold on, this shearing stress over here, right, will generate a clockwise direction. Sorry, counterclockwise direction. So counterclockwise direction, so this is the counterclockwise direction. So over here, this is your point Z. Okay, that is your point Z over there. So this is our point Z. And if you look at point X, right, now we look at point X. Okay, we look at point X. And this arrow over here, okay, if we put your finger at the center over here, will generate a clockwise rotation, right? So when there's a case, this over here is clockwise, so this is your point X, okay? And some of you will ask me, where is our point Y, okay? So point Y has 0 normal stress and 0 shearing stress. So over here at point 0, over here, this is your point Y. Okay. So you join X and Z first. Okay. You cannot join X and Y. You cannot join